let's take a few minutes and look at how we complete inference for two population means. So means involve using t-scores, and in this context, we're not going to be looking at simply one population, we're going to be looking at two. So, is there evidence that eating chocolate will change students' average pulse rate? Now, notice the way that I wrote this, I'm looking for evidence of a change. So maybe eating chocolate because chocolate has caffeine in it, maybe that will increase your pulse rate. Although maybe the opposite could occur. Maybe people that like chocolate will eat chocolate and then they actually go to their happy place and they feel more relaxed because they're enjoying something that they really like, chocolate. So let's see if we can just find evidence of a change. I'm not particularly sure which direction it might be. So when you don't have, before you do your experiment or study, an idea of which direction that change might occur in, just look for evidence of a change or a difference. So we really did this experiment. This is real data. So students were randomly assigned into two groups. So the treatment group consumed 2 Hershey's Kisses, waited 5 minutes, and then measured their pulse rates. So that treatment group is summarized down here as the chocolate group. So there were 43 students in that group. So after they consumed the Hershey's Kisses and waited 5 minutes, this was their average pulse rate. This is the standard deviation. Here's a histogram of those pulse rates. So the lowest pulse rate was in the 40s and the highest rate was in the low 100s. So the control group simply measured their pulse rates. So this is the control group. So there were 48 students in the control group. Their average pulse rate was 72.6 and their standard deviation was 10.4. These are beats per minute, are the units for these sample means and sample standard deviations. So notice these are two distributions of quantitative data that we could compare. We could compare these shapes. We could compare these centers. We could compare these spreads. So that goes back to the ideas in analyzing one variable data. That's our very first unit. So notice the shapes look somewhat similar. They both have central peaks. They both look somewhat mound-shaped, if you will. There is a difference, I suppose, in the centers. The chocolate group actually has a slightly lower center in terms of a mean. So the mean for the control group is slightly higher. The mean for the chocolate group is slightly lower. So I would offer, in terms of their spreads, be careful because you can't calculate the range from the histogram because you don't know the numeric value of the highest observation and the lowest observation. So based on the data that I've given you, because these are reasonably mound-shaped and reasonably symmetric graphs, I don't necessarily see outliers in any of these graphs. So maybe there's a gap here. I'm not really sure if I would call that a gap. And the truth is, if I simply change the window settings and instead of putting 5 beats per minute within each class, if I made it 4 beats per minute, that gap might actually disappear. So the truth is, I'm not convinced that there's necessarily a gap right there, but there certainly aren't any outliers in either of these data sets. So probably the safest thing to do here would be to compare their standard deviations. So it looks like the treatment group has a higher standard deviation in terms of beats per minute than the control group. So, but understand, simply by comparing the sample means, I can't really make a conclusion about what might happen to students in general. Because look, I agree that the chocolate group has a lower sample mean in terms of their pulse rates compared to the control group. But is this difference large enough to give me evidence that in general eating chocolate will change students' average pulse rates? So in order to find evidence, I need to complete a significance test. So notice I'm going to write my hypotheses. So mu chocolate, that's the average pulse rate of students that eat chocolate. Mu control is the average pulse rate of students in the control group. So a small detail, if you were to ever define your parameters, it's important that you use present tense when you define your parameters because the parameters are not about what has happened, past tense, in the sample data. The parameters represent the truth in the population, and I need to write hypotheses about what those truths, how they might be related to one another. So in the null hypothesis, if this treatment really doesn't have any effect, I would expect the difference between these two population means to be 0. So I'll say mu chocolate minus mu control equals 0. And we're looking for evidence simply of a change or a difference. So that means our alternative would be a not equal to alternative. So mu chocolate minus mu control not equal to 0. So in terms of our conditions, just like in one sample situations, we have to consider randomness and independence and normality. Now, important, this is an experiment. This is not an observational study. We have random assignment into two groups, a control group and a treatment group. I am not randomly sampling from two populations and trying to compare the means in those two populations. So this is random assignment. So because I am not randomly sampling from two populations, I don't need to check for independence. I don't need to check the 10% rule in this case. So this is an experiment. So for randomness, we have random assignment. To a treatment group. That's the eating chocolate group. And a control group. That's what makes an experiment when you have random assignment to a treatment group and a control group so that you have a basis for comparison. Because we have not randomly sampled from larger populations, we can't check the 10% rule. So then for normality, let's look at the sizes of the groups, the number of subjects, experimental units, if you will, people, students in each group. So the chocolate group has 48 subjects. Rather, the control group had 48 subjects. The chocolate group has 43 subjects. So notice the chocolate group, that's considered a large sample, if you will. That's certainly greater than or equal to 30. And in the control group, 48 is also greater than or equal to 30. So notice, because we're working with means, we don't have successes and failures where I can consider counts that are greater than or equal to 10. This is not categorical data where there are successes and failures. This is quantitative data because I'm looking at pulse rates. When you are working with quantitative data, we will work with means, and that's where you have to compare to 30, because not just in one group now, because this is a two-sample situation, in both groups I need 30 or more observations or subjects or experimental units. Since both groups have a large number of subjects, 30 or more, this means that the central limit theorem applies. So note, if the number of subjects or experimental units in each of these groups, or if the sample sizes in an observational study, so if the number of subjects or experimental units in each group, or the sample sizes in an observational study, were not considered large, if they weren't 30 or more, we would need to verify that there are no outliers and no serious skewness in either of the two data sets. So, bottom line, it doesn't matter whether you're building a confidence interval or doing a significance test. If you have quantitative data, you should always look at your data, consider your data, graph your data before you just jump into doing some type of test or confidence interval or some type of inference procedure. So we have our hypotheses, we've checked our conditions. So now it's time to go on and calculate our statistics. So when we did significance tests for one mean. Those were one sample t-tests. Well, now we are going to do a significance test where we're using two means. So shockingly, the name of this procedure is a two-sample t-test. We're going to find the t-score, the degrees of freedom, the p-value. We can get all of that from our calculator. So if you press Stat and go to Tests, we're going to go to two-samp t-test. So we are going to enter then the statistics. So choose the statistics option. The data option would be if you have data in lists in your calculator, you could specify those lists. So here, what I have done, I've summarized the data, so we will enter our data. Important then, when I wrote my hypotheses, I wrote the chocolate group minus the control group. So that means that the data from the chocolate group has to go in as x1 and standard deviation for 1 and sample size for group number 1, if you will. The control group would be the second group. So for the chocolate group, their mean was 70.6. Their standard deviation is 13 beats per minute. There are 43 in that group. In the control group, their mean was 72.6 beats per minute. Their standard deviation was 10.4 beats per minute. And their sample size is 48. So this is a not equal to alternative hypothesis. And very important, we will not do pooling in this class. So leave pooling as a no. Always leave that option as a no. So at this point, we're ready to calculate. So here is our t-score. Here is our p-value. Notice here's the degrees of freedom, which is actually a decimal value. We'll talk about that in a second. So here are the two sample means, the two sample standard deviations, the two sample sizes that we entered previously. So for our purposes, it's important in terms of the statistics. It's important to document the t-score. So I'll write down the t-score as negative 0.804. So the degrees of freedom, I'm going to write that down as 80.36. And then the p-value is I'll write that as 0.424. So we'll come back to this section in just a second, but what I want you to realize, trust the calculator in order to get your t-score, your degrees of freedom, your p-value, but very important to name the type of test that you are using. And then the truth is we can make our conclusion like we would for any other significance test. Our alpha level is going to be the 5% level, so you always compare your p-value to your level of significance. So in this case, we have a very large p-value with 0.424, which is well greater than the 5% level of significance. This is not unlikely. This is not an unlikely outcome if the null hypothesis is true. So that means we do not reject the null hypothesis. We fail to reject the null hypothesis. And then notice my strong suggestion is that you simply copy the words. So look, the question was written, is there evidence that eating chocolate will change students' average pulse rate? Well, no. So this means we don't have evidence. That word evidence is the signal that you need to use a significance test. Sorry, I guess I should have given you another line here. So we don't have evidence that eating chocolate will change students' average pulse rate. So bottom line, if you want to put context into your answer, if you want to interpret the alternative hypothesis accurately, the simplest way to do that is just to recycle the words in the question. So I do want to take a second and show you where this t-score comes from and where this p-value comes from, and at some level where the degrees of freedom come from. But the bottom line is, please use technology. Please use technology in order to execute these significance tests. That is absolutely the way to do this successfully. So first of all, if you were to complete this test by hand, so what we need to do is to create a t-score. We're working with means. So our t-score, we are going to take the actual difference between our sample data. So now be careful. Be careful. So we have done, our null hypothesis is about mu chocolate minus mu control. So I need to take the mean for chocolate minus the mean for the control group. I have to subtract in that same order. So the difference that I am interested in standardizing is the difference between the chocolate group and the control group. So that's the mean pulse rate for the chocolate group. Here is the mean pulse rate for the control group. So this is the difference that I am standardizing. So what I need to do is subtract the mean for the difference between these two sample means in terms of the sampling distribution. So understand, we have, from a few units ago, we have formulas for the mean and the standard deviation when we are working with the difference of two means. So this comes straight from the formula sheet. So when you are working with the difference between two sample means, the truth in the middle, the mean of the differences of those sample means, is the truth. So in our null hypothesis, our chocolate and control groups we have assumed have the same mean, so the true difference is 0. So I'm going to subtract 0 when I standardize this difference. And then I need to divide by the standard deviation. But we already developed a formula for the standard deviation. So in the sampling distribution, it's the real standard deviation of the first population squared divided by the sample size from that population, plus the population standard deviation from the second group squared divided by the sample size that was selected from that population. Of course, we don't know those standard deviations, so we need to use the standard error instead. So that's where we take the standard deviation from the chocolate group and square it and divide by the sample size from the chocolate group. And the same thing from the control group. We'll take that standard deviation, square it, and divide by the sample size from that group. So we can use this straight from the formula sheet. So the standard deviation from the chocolate group is 13. So I need to take that and square it and divide by the sample size from that group. That's 43. Then I need to take the standard deviation from the control group, which is 10.4. I need to square that, and I need to divide by my sample size for the control group. That's the 48. So if you wanted to calculate this t-score or this standardized score by hand, that's the work. And now we have to dump it into the calculator, and again, we should get something relatively close to this negative 0.804. Let's see how accurately I can put this into the calculator. It's not quite as simple as it looks. So I'm going to take the 70.6 minus the 72.6. So, wow, well, obviously I should have actually paid more attention. That's pretty easy. And subtracting 0 just gives me negative 2. So that's my numerator. Then I need to divide by my standard error here. So I'm going to take the 13 squared divided by 43. And then to that, I need to add the 10.4 squared divided by the 48. And there we go. There's the negative 0.804. That's where that value came from. It's important to at least show you this calculation by hand. It is important that you realize that the calculator is just relying on the methods or the strategies that we've already developed. It's just there's too many places to make mistakes here. And instead of doing it by hand, then let's rely on the calculator to develop those statistics so that we can focus on communicating an appropriate conclusion. Now we're not done. We need a p-value. So remember, when we're working with the t-distribution, we have to calculate the degrees of freedom. Now, I will tell you something. The degrees of freedom in a two-sample situation are quite complicated. This is actually the formula. If you were to complete this test by hand, The actual formula to find the degrees of freedom that the calculator uses is complicated. It's given at the right. I actually took this picture out of the previous version of our textbook because it's complicated enough that it's not even included in our current version of the textbook. If you had to do this by hand, that's why, by the way, that's why the degrees of freedom end up being a decimal value. So it was important to write it down. You'll see why in a second, because I need to use this degrees of freedom with this t-score in order to calculate the p-value. However, if you had to do it by hand, a more conservative way to do this would be to take the smaller sample size and subtract 1, and you could use that as your degrees of freedom. So between these two groups, the smaller sample size is 43. 43 minus 1 would be 42. If you wanted to use 42 degrees of freedom, you could also do that. It will give you a slightly different p-value, but the truth is it will give you, if you will, a p-value that tends to be larger than it really needs to be. That's okay. That isn't something you're going to have to worry about doing because you really should use your calculator in order to do it. So now understand, this is a two-sided test. This is a not equal to alternative. So we're going to calculate our p-value in one direction, but then we need to double that area. We have to double that probability in order to get our actual p-value. So let me draw a picture then of the t-distribution. So here is our mean, if you will, of 0. In the t-distribution, we would also have a standard deviation of 1. So in this case, then, our standardized score is at negative 0.804. So I'm going to put down that boundary at negative 0.804. So remember, a p-value is the likelihood of a sample difference this extreme or more extreme if the null hypothesis is true. So if the null hypothesis is true, the real difference in the population means is 0. So the actual difference between the sample means is negative 2 beats per minute. Well, what that really means is 2 beats per minute or more difference. So that could be in the negative direction or in the positive direction. We are going to use a command in order to find the area in the negative direction, but as or more extreme than a difference of 2, it could also be a difference in the positive direction, so we will draw that in just a second. In order to calculate this, you have to use the tcdf command, and the tcdf command requires the degrees of freedom as an input in order to get your p-value. This is all the more reason why we want you to use your calculator to do this instead of doing it by hand. So here is the tcdf command. So the first thing that I'm going to do is to put in a lower boundary. So in this case, I'm going to put in, you just need to put in a value that is negative, and a large negative value, negative 100, negative 1,000. Either of those would be perfectly fine. I'll put in negative 1,000. So my upper boundary is negative 0.804. Then the next thing that you have to do, you have to put in the degrees of freedom. So we're going to use the actual degrees of freedom so we can confirm this p-value here. So we'll put in the 80.36. Again, I slightly rounded those degrees of freedom a little bit, so the p-value will be off a little bit. So we'll call this p-value 0.21, we'll round that to 0.212. Now understand, you might be thinking, Mr. Schaaf, that's not the same thing. Yeah, I know that. Because we've only calculated as or more extreme in one direction. So remember, the alternative hypothesis is a not equal to alternative. So a difference as or more extreme than this means 2 beats per minute difference or larger in either direction, in the negative direction or in the positive direction. So it could also be 0.804 or above. Now, using the symmetry of this distribution, that's also going to be 0.212. And then notice, if you take 0.212 plus 0.212, that gives you the 0.424. That gives you our p-value. I want you to see how everything connects and fits together. That's such an important idea. But bottom line, we are encouraging you strongly, please use your calculator in order to do these calculations. Going through all this work is not required. That's not the point. The point is to make a good conclusion by using data that are appropriate for the question. So, bottom line, just for fun, I will show you, if you didn't have the 80.36, the degrees of freedom that you would want to use is 42. So I'll show you that same command using the 42. And what's important here, I'll put in my large negative number, I'll put in my negative 0.804, and then I'll put in the 42 degrees of freedom. So notice you get a slightly different value. In this case, it's 0.213. So if you got 0.213 on each side, again, that's using degrees of freedom of 42. So if you add those together, you get 0.426. And the difference in the p-value isn't enough to make a difference when you make your conclusion, because remember, our goal is to compare to that level of significance. So whether we're comparing to the 0.424 or the 0.426, either way, we have a very large p-value, well larger than 5%. So we're going to fail to reject the null, and we don't have evidence of the alternative. So one last thing in your calculator then, let's look at how you would find a confidence interval for the difference between the mean pulse rates for students that do and don't eat chocolate. Again, notice to interpret this confidence interval, by the way, you can just copy those words. We've already checked the conditions. They're the same. We want a 95% confidence interval so that our confidence interval can correspond to our significance test up here. So the bottom line, all you have to do at this point is to write down the name of your procedure. And this is not a test, so this is not a t-test. This is a t-interval. And because we're using two means, we would write this as a two-sample t-interval. So we'll go to the calculator to actually calculate the two-sample t-interval. So stat tests. Scroll down carefully. So here was the two-sample t-test. I'm going to keep going. I have to find two-samp t-int. There it is. Two-sample t-interval. And notice the calculator saved the statistics for us. So here are the data from the chocolate group. Here are the data from the control group. Our confidence level is 95%. We don't want to pool. So we can simply calculate and we will get our lower and our upper boundaries. So the lower boundary, forgive me, I'll write it here. So the lower boundary, we'll call that negative 6.9. The upper boundary, we'll call that positive 2.9. I'm just getting that straight from the calculator. Sorry about the glare there. Notice the degrees of freedom, again, are 80.36. So important that you write that down. It's just like with the test. So we're ready to interpret our confidence interval. So remember, with a confidence interval, you always start by indicating the level of confidence because that tells you the accuracy level of the method. So we are 95% confident. That. And then let's copy the words. The difference between the mean pulse rates. So because this is a two-sample situation, we're looking at the difference between we're trying to capture the difference between the two actual population mean pulse rates. So we're 95% confident that the difference, so that word is important, the difference between mean pulse rates for students that do and don't eat chocolate See how I cheated there? I was about to write the word wrong. So eat, that's do and don't eat chocolate is between negative 6.9, I'll use units here, beats per minute, BPM beats per minute, and positive 2.9 beats per minute. So understand the reason that this confidence interval, then, we get the same conclusion as on our significance test. Notice what's captured in that confidence interval. The lower boundary is negative. The upper boundary is positive. So a difference of 0 beats per minute is captured in this confidence interval. Because that is in the confidence interval, we fail to reject the null hypothesis. So remember that the null hypothesis is that the real difference between the mean for the chocolate group and the mean beats per minute for the control group was 0. So that 0 is actually captured in the confidence interval. I can't reject it because it's in there. So we fail to reject the null hypothesis. So again, we don't have evidence that eating chocolate will change students' average pulse rates. Exactly the conclusion that we wrote above. So remember, just a note then, it has to be a two-sided significance test. It's important that two-sided significance tests, those can be completed using a confidence interval. So a two-sided test and a confidence interval, if you will, correspond in this context. However, important advice on the AP exam, you should build a confidence interval only when asked to do so. If you need to build a confidence interval, the question will ask you to do that. So whenever a question is stated asking you if there is evidence of a particular result, a significance test should be completed. That's one of the reasons why when we write the conclusion in a significance test, I want you and expect you to use that word evidence. That's the key to knowing what method that you should use, and it was the third word in the original question in this lesson.